Thank you, Manfred, for the introduction. I certainly don't know everything, but I try to learn and know a bit. So thank you for joining this presentation. I wish we had a more face-to-face contact, but this is how it goes. This presentation will be kind of unusual, probably because it's not really about how to use Trino, but more of a lesson learned that we learned the hard way in the Trino project. And I hope it's useful not because it pertains directly Trino users, but more because it pertains Java development in general. So hopefully this is useful for you. So we will talk about caches and invalidations and race conditions. So I hope those terms sound familiar to everyone, including myself. So during the presentation, I will tell you, well, what Trino is. I guess I don't need to introduce, but more about like why it uses caching and what it uses caching for. Then I will tell you more about the problem statement and what we are solving, what the problem is actually. And also, I will tell you about how we were solving this problem. Before we dive deep into the caching and the problem itself, maybe a few words about like why you should consider listening to me at all. I'm with the project. I'm involved in the project for 7 years now, almost without 1 month, and being a Trino maintainer and a so-called committer back then since 2017. I made a bunch of contributions over the time, so there's like a big number of commits, you may say, but actually this is less than 2 a day, so not that much. But that's actually, doesn't mean much. That's basically the proof that number of commits doesn't mean much. But what I'm more happy about is my involvement in the reviews and helping people use Trino and contribute to Trino over time. So back to the topic. Trino and caching history in Trino. So actually, Trino is not the first project library application that uses caching. Caching is a known technique for like since Renaissance actually. So let me start with a quote from chief architect of the globe. Let me read it out, hopefully correctly. To cache or not to cache? That's the question. Whether it is wiser for code to endure the slings of latency or take action against a sea of requests and assure to hit, perchance to miss. Aye, that's the rub. For this, in that cache hit, what bugs may come. I guess you are generally familiar with this quote, but I thought it would be interesting to remind about that. So Trino is not as old as Renaissance, of course. It started in 2012 in August, and actually I checked the history. It was not later than 2 months since the project started, where the first cache usage was added to the project. That was actually in the Raptor connector or native connector, so-called back then. First cache with some kind of invalidation. I will talk about why invalidation matters later, but first cache with some kind of invalidation was added only for 4 months later, so half a year since project started. That was probably, the thing, caching Hive Metastore. And it was basically a read-only use case, so the invalidation was there for debugging purposes only. Year and a half later, we have cache. We have the Trino Views support. So the called Presto Views at the time, of course. So this is the use case where we create metadata in the metastore. So this is read-write use case, and read-write use case and caching obviously requires some caching validation. So this is where it was added for the first time. And over time, there were many different applications of caching in the project. And currently today, there is over 100 different places where we utilize caching for various purposes. And in all those places, we use very well-known library Guava to implement the caches. So why would you want to use caching? Well, there are a variety of use cases or reasons why you would want to use caching. Generally, the most typical case is when you want to reduce the load on the remote system. So instead of reading a certain thing multiple times, you read it only once, you remember what you read, and you use it for the next requests. The other connected but maybe less obvious is to make sure there is your processing latency is decreased. So you basically want to take the slow calls to remote system of the critical path. So for example, let's say you load the information about tables or partitions from Glue Metastore or HMS Metastore, and it takes time. And for a low latency use case, you want this information to be already present on a system, on a Trino cluster before the query starts, so that you don't wait at all for the communication with the remote system. So it's not really about reducing the load, but more about reducing the time. And for that, you not only want to do caching, but also you want to refresh the values. So they are not only cached, but also staying up to date over time. The other example the other situations where we use caching in Trino is, for example, in code generation. So we have an expression that comes from the query, and we generate, for this particular expression, we generate a dedicated specialized Java class that processes the expression, and this in turn allows a Java just-in-time compiler to generate optimal machine code for particular SQL expression. And obviously, this process is not very cheap. So generating the class is not cheap. Getting the Java just-in-time compiler, profile the class, understand what machine code it should generate, and then generate that is not very cheap either. So in order to reduce the amount of CPU time we spend on the preparation for processing the query, we use caching. So if the same expression appears in multiple different queries, or like the queries are repeated, we reuse the classes. We don't generate them over and over again. This not only saves the CPU time on the bytecode and machine code generation, but also reduces the pressure on the meta space where all those classes are being held. Yet another use case is ensuring the strict consistency. So for example, when we plan a Trino query, we have the per query context within a transaction, and all the requests to metadata, to labels metadata, they are served from this query scope cache. And that ensures that if you reference, for example, if you reference a table multiple times within a query, all those references will effectively be resolved to the same table at the same state, at the same version, because they're basically referenced once and served from the cache. And this is important from query data processing consistency requirements, stuff like that. Yet another use case, probably more esoteric, is ensuring things happen exactly once. For example, when you look at how Trino manages query context or task context on workers, it very cleverly uses caching to provide an idempotency for task creation, and especially for the query context creation on each of the worker machines. So summing up, all the different use cases, all are served with caching library, And so this is pretty generic and generically important. This is exactly why I think it's generically important and also outside of Trino. Take a look at the code, how to use a cache. Well, cache is basically a map that's leaking the values over time. So you would declare it as a map, and then you need to declare that the expiration or how slowly or how quickly the entries are expired. So this is pretty standard Java code that you probably saw many times, and this is basically how you get the value from the cache. You look at the cache, there is value, okay, use it. If there isn't a value, you load it, put in the cache. Pretty standard Java code. I'm sure you saw that many times. And well, if you on the left there is still the same code that for reading, and on the right you see how if you write to a cache or to a remote service, you probably want to invalidate the cache to ensure that subsequent read will go again straight to the remote system, read the fresh value, and serve the fresh value. So basically, typical code that loads the value from the cache on the left side and stores the value, invalidates the cache on the right side. Wait a sec. So going back a bit in history, there was a famous quote, you probably heard it. There are only two hard things in computer science: caching validation and naming things. Did we miss something? It looked simple, but this guy says that it's actually hard. Well, yeah, we missed something. So we missed something about concurrency. Let's imagine that there are two threads executing the get and the put. First one executing the get, second executing the put, and they interleave just as the numbers show. So the first thread checks the cache, there isn't an entry, it loads the value, but it doesn't put into the cache yet. And then the second thread, it stores the value into the remote system, it invalidates the cache. Okay, and then back the first thread puts the value into the cache already after the invalidation. So invalidation didn't discard anything because there wasn't anything in the cache yet. But the load and the put puts the stale value into the cache. So now, if you think about that, what happens next is that any subsequent read from the cache will see a value in a cache, and it will be the wrong value. And then if the cache, for example, expires after 1 hour, it means we have 1 hour for inconsistency state in our application, which from like eventual consistency perspective is pretty bad. Like waiting 1 hour for a system to heal is pretty too long. Can we do better? Yeah, sure. Well, first of all, we use a pretty verbose pattern for inspecting the cache and loading the value. And there is a dedicated method that basically encapsulates all of that with one simple call. So it should solve the problem, right? Right? I mean, it should. But, you know, there are only two hard things in computer science, caching validation and naming things. And actually, you know, the code is probably looks like named properly, but it still suffers from caching validation, although we don't see that yet. It's very not obvious. And actually, for the Trino project, it took several years since we added the caching with invalidation until we realized that we have concurrency and consistency problem due to the caching. And this was realized only in 2022 by my colleague Zeszek. And he pointed out that there is a problem that this invalidation is still racy, even we have this code wrote a better way, and points out to a Guava issue, which says that this invalidation is racy because the invalidate cannot invalidate the value that's still being loaded. It's not loaded yet. So the value that's not yet loaded is not visible in the cache. You can invalidate that. And this is the very source of the problem. And as you may notice, these are the screenshots that I did just yesterday. The Guava issue is still open after several years, and the Trino issue is closed. So there surely is some solution. So let's try to find a solution. How did we solve that? So before trying to uh, find a solution, we had a test. We added a test that clearly deterministically reproduces the problem. And for the test, we put 4 different strategies of cache invalidation that we use in various places in the code. Sometimes we invalidate with a specific key. Sometimes we invalidate a bunch of keys. Sometimes we inspect the cache and invalidate all the keys that match a given predicate. And sometimes we just invalidate all of the cache. So the first example for the first invalidation strategy would be when you load a table by name. So if we change a table, we basically invalidate the table cache by this name. But we also invalidate the table listing. So we just invalidate all of the cache. And having the test show that the Guava caching library is susceptible of the race condition in all the 4 different strategies that we have. And we found out that actually Guava folks recommend to use the caffeine library that's still like better maintained or more actively maintained. So we tried to use that. And the results weren't very satisfactory. So first of all, you see that when you invalidate all of the keys, it still exhibits this stateless problem, this recognition problem. And more severely, if you invalidate a particular key, it attempts not to fall into this trap of race condition, but it does that by waiting for the load to finish. So imagine that you invalidate the cache and all of a sudden this operation is no longer constant time, but instead it loads for some other thread to do some communication with the remote system. It felt bad, and it's definitely not what we wanted. Fortunately, caffeine comes with actually 2 flavors: the typical cache and the async cache. The async cache has this disadvantage that it uses futures everywhere in its API, but it has the advantage that this passes the test. So hey, we should be back home with that. But that couldn't make a fair presentation. So well, we stressed the implementation further. We ran the test multiple times, and we realized that no, it doesn't really solve the problem. It just makes the problem less probable to occur, but the problem is still there. And in Trino, we really strive for correctness, not almost correctness, but we strive for correctness. So that wasn't really satisfactory for us. So unfortunately, we couldn't use the library, but I wish we could. So I mentioned futures in this async cache. So why there are the futures? The futures allow you to separate insertion into the cache from the loading. So looking at this code example, in the first operation, we create a new future. We don't load the value yet, and we load later. So what it does is, if someone wants to invalidate the value in the future now, is already in the cache, so it can be invalidated. So using futures actually solves the invalidation race condition, which is very nice. But it has some drawbacks. First of all, it's very verbose. Remember this one-liner where we just call get cache with a lambda to load the value. Now we are back to this more verbose code pattern that we had initially. Second problem is that you don't, if there isn't an entry in the cache and 2 threads concurrently ask for the same entry, you don't get a load sharing, which you get for free when using Guava. So both threads will make a remote call. And of course, you can solve that. You can select one thread to do a load and the second thread to wait for the first one to finish. But then it gets really complicated because you need to also propagate the failures, and you also want to another attempt to start the load afresh. So you also need to remove those features from the cache when the load doesn't work. So that gets really complicated. Actually, we did implement that solution for some time, but then we removed that. Another problem it exhibits is that you cannot use the refresh after write because the cache no longer refreshes. So you remember about this use case where you want query planning to have as little latency as possible, and you want to use proactive refreshes so that the values are always present and up to date. So it doesn't work very well. And moreover, it doesn't work with weighted caches. You cannot say, oh, let's say I take into account how big is the cache entry. For example, in directory lister in Hive, we do that to limit the memory pressure of the cache. So the next solution we thought about is using generational tokens. So basically, this is conceptually very similar to futures, except that you basically insert a token. A token is just an object. It has identity equality semantics, so they just don't hold any state. And instead of one cache, you have two caches. So you insert the token first, you do a load with the token, and invalidation invalidates the token. By using the cache to load, you get the load sharing and other invalidation mechanisms for free, which is very nice. The disadvantage is that you somehow need to clean the tokens, otherwise you would have out of memory. And you cannot just do that with a cache again, because you cannot, for example, weigh the tokens. You cannot see how big they are because that's a separate cache entry. So the solution would be to create a persistent map for the tokens and then use cache listeners to propagate eviction from the cache to the tokens. But actually, that's if you compare this with a future-based approach, this is way more complicated. It may work better, but remember, we have over 100 different places where we have those caches. So it would be infeasible to change every of those places and convert every single cache out of this 100 to be two different caches. So what we wanted to do is we wanted to create a library that solves the problem. Again, this is a typical code that declares a cache and uses the cache. This is how you use Guava. And basically, this is how you use evictable caches, which is how we call the library. You basically use a different builder that follows this completely same API as the Guava one. It has the same capabilities, maximum size, weighing, time-based expiration, refreshes, and bulk loading, load sharing, and whatnot. And the only thing it does is it doesn't exhibit this race condition problem by using tokens internally transparently. So that's hopefully interesting, but you may wonder how that applies to you and how you can use that. So you probably don't want to re-implement that because it's actually not very trivial, I would say. Or maybe you want to implement it because it's not trivial. So have fun. It's a very interesting exercise. But if you want just to use the solution, well, you can use the Trino cache as an artifact in your applications. And basically, this gives you this evictable cache builder and you just can use it and all the other interfaces. There's Guava interfaces. Remember, however, you probably may remember this slogan that Trino is not a library. So you may wonder why I'm advising you to use the Trino as a library. Well, that's probably the most convenient, but I'm not. Because I can't guarantee that it doesn't break. So for your convenience, I package that as a separate library, so you can use either, whichever is more convenient for you. And last but not least, there's obvious questions like, how do I find those 100 different use cases, 100 different caches, and make sure every single each of them is updated? And moreover, how do I keep my code updated? Because otherwise, I would need to review every single PR and make sure there are no uses of the wrong caches or race condition susceptible caches. So obviously we wanted this to be automated. In Trino, we use modernize the library for a lot of, we use actually a couple different libraries for static code analysis, and one of them is Modernizer. And the Modernizer library allows you to write a simple patterns, basically using the JVM machine level signatures of method that you want to prohibit. So basically what we did is just prohibit the cache builder, the Guava cache builder methods requiring to use evictable cache builder build methods. And that means that all the use places of Guava caches are automatically flagged, reported, and we don't need to remember about that. So if you want to use a library to solve the problem, or you roll out your own solution, I definitely recommend automating the finding of all the offending places. We talked about Trino and why it uses caching. I do believe it's really pretty common to use caching in all the applications, not only related to Trino, but generally. I do believe many caches require invalidation, and invalidation is really as hard or even harder as naming things. And this is lesson hard learned that we had in Trino. And I hope you enjoyed the journey, how we solved that, and hopefully you can find it useful for solving this problem in other applications as well. With that, we have still time for all the questions.
Yeah, thank you so much, Piotr. That's super interesting. It was great also watching the chat going off with like geeking out with you and like diving into the depth of the Java code and like appreciating your reading of the Shakespearean quote. I have to ask, did you like create that Shakespearean version about caching, or did you find that elsewhere?
I must admit I did what's very popular these days. I logged into chatopenai.com. I asked that guy to generate something, but it was too long, so I had to manually edit that to make it nice.
Very nice, very nice.
So it's a teamwork.
Yeah, that's ultimately what IntelliJ and whatever IDE you use is, and AI is like the next level of tooling. So it's great, awesome. It's really cool. People also were talking about your quote about the hard things in computer science, and they mentioned that you missed the off by one errors. So it was quite fun. Questions wise, I have a couple. There weren't any much in the audience themselves, but I think maybe wanted to just clarify with you. So this caching that you're talking about is obviously Guava based, or like is like basically it's caching in the JVM. So that's all in memory then, right?
Yes, this is in-memory caching using the Guava library.
And then if that's the case, how does that work how does that affect your usage of those caches across the workers in a Trino cluster, right? Like like there's no such thing as like a shared JVM that runs across the cluster. There's an individual JVM in each. So does that mean every worker and coordinator, they all have their own caches? And then you mentioned that there's like over 100 usages. So there's like caching all over the place, basically.
Yeah, that's a very good question. So yes, you're correct that this is in-memory caching, very much like a map in Java, just a leaky map. And there is no concept of a shared cache that's internal to Trino. And actually, I don't think we have a good use cases outside of the data processing. So you remember certain use cases. So we use caching for like metadata handling. Caching the metadata, this happens on the coordinator only, so the workers doesn't need to do metadata handling with the metastore, for example. We use code generation, caching for code generation. That happens on each worker individually, and that would probably be a bit overhead to share that. That would be complicated, but with not very much gain. So there are use cases where in-memory caching is basically the best, and there are use cases where it's certainly not the best. For example, if you do data caching, you certainly want to be location aware. If you do on-disk caching, you need to route requests to a particular machine and stuff like that. So what we are talking here about is really generic in-memory caching. And if you roll out something that's dedicated to data, you probably basically implement the same concept, but with much more thought and more elaboration. It's getting much more complicated, and you implement it explicitly. And you may use Guava caches along the way for some reasons. For example, caching the status of files on disk, for example, on each of the workers. But then the whole concept will be a distributed solution, and this distributed solution requires an explicit code to be written.
That's cool. Eh? Yeah, like so we just scratched the surface literally with this caching that's isolated in each worker in the JVM, and then there's much more layers on top of that, really. So that's amazing.
Certainly.
Also, yeah, it's also like very much appreciated that you open source this into a SEP and evictable cache library. There are people in the audience who are already saying that.
Obviously,
that's cool.
We also offered a solution to contribute back solution to Guava. This probably would be actually much harder. The problem is with Guava is that it's not as actively maintained as it used to be. So I don't know whether they would want a patch. So the question is still there, and they still didn't reply to that question. Implementing a solution outside is actually turned out to be simpler, more practical. So we just solved the problem for us, and we are happy to share the solution with everyone else.
Yeah, maybe it's worth filing a ticket on the Guava library, but like, yes.
No, it's already there for 8 years.
yeah, but like leaving a comment that here's a solution that might be suitable, and you can pull it into upstream. But yeah, working with upstream is always tricky. A lot of these projects are more or less active, as you mentioned, and luckily we are in the Trino ecosystem where we are very active, and we appreciate all the changes and the PRs flying in. We just kind of released yesterday, and more is coming already in, and it's really amazing. So thank you, I think, from the community and to you for all your hard work and helping on the pull requests and stuff like that. It's not just wrong evidence. So with that, we're going to jump to the next talk.
Thank you very much.